All right. So today we're going to talk about Navier Stokes. So let's get started. I'm going to go over the reading questions first. Several of you had some great reading questions. There's my sheet. There's my sheet. Okay. Those first two pages confused everybody. So that's cool if you felt confused by the first couple of pages, the first derivation. That's okay. We're going to get through it, and then you'll be able to do it. So all of that stuff, as confusing as it was, is, I think, pretty important, and I'm going to make you do it. I want everybody to get familiar with that, because that whole section is about taking concepts that are kind of abstract and spatial and turning them into math. And that's, one of the things that you want to get good at as a physicist. This is how we're going to do it, is with Navier Stokes and continuity and all these other equations. I think I'm the only one teaching in here, so I get to leave up my stuff. So the equations that we're going to be focusing on are continuity and Navier Stokes, and these are the important ones, which I'm going to leave up. We're going to talk about all of this thing today. And also internal energy, which we're not going to use as much, but it is a third complete independent equation. These three equations define the universe. You don't need any more. That's everything. If you have something complicated in your universe, it goes into this equation. Sometimes in this one. Only in this one if you have like a nuclear explosion or something. This is mass conservation, so the actual mass density very rarely changes. Or if it's relativistic, which we're not doing in this kind of class. Okay, so Navier Stokes is the one we're going to spend most of our time with today. So, okay, so this one, everybody kind of hated this equation. I'll talk about this in detail when I get there. This is like a quarter of everybody was like, please explain equation 5-6. So I'll do that, but I'm going to do it later. Let's see the second question. One of you asked about irregular flows. So in the Poiseuille, do any of you speak French? I don't know how to say that word. I think it's Poiseuille, but I always screw it up because it's French, and I don't know how French works. So when you have a pipe flow, if the equation, and I'll derive this equation again too, because that's another one that I think is important. This pipe flow equation works when the flow is laminar. And it breaks down when the flow gets irregular. And I'll talk about why a little today, a lot later. Yeah.
Can you define laminar?
Yeah, laminar means it's not irregular.
Okay. Yeah.
Laminar means smooth. I bet that there's a really good, rigorous definition. Yeah.
When you say irregular, do you mean turbulent?
That's where I was going to go. Hang on one second. So put a pin in that question. So there's probably a formal definition for a laminar, but I don't know it off the top of my head. This means that, well, probably what it means is all the streamlines are parallel and never try to cross. I'll talk about what a streamline is a little bit, but it's basically a streamline is where the velocity is going. There are some subtleties that I don't care about. A streamline is where the velocity is going. So if all your streamlines are parallel and smooth, then your flow is smooth. But as soon as these get kinked or distorted and the flow becomes irregular, then problems happen. Now, irregular can mean a couple of things, and this is a question that a couple of you had asked. Does that mean chaotic, or does that mean turbulent? It doesn't necessarily, but it's getting there, kind of. So the flow is very smooth when the flow is slow, and it's turbulent when the flow is very high. Somewhere in the middle, there's a transition where it's not really turbulent, but it's also not something we can write down and predict. So irregular is not necessarily the same thing as chaotic. Chaos has some particular properties. Chaos has structure at all scales and isn't differentiable in time. So we'll talk about chaos when we get to turbulence. So it's not necessarily chaotic, but maybe it is. some of the time. Probably is almost definitely going to become chaotic eventually. So irregular is not chaos, but chaos is irregular. Chaos has more baggage with it, and turbulence has some more baggage with it in addition to just being not smooth. But smooth flow is easy to do things with. As soon as it gets not smooth, it gets hard to deal with. When it's fully chaotic and turbulent and you can really rely on some randomness, then it gets a little easier again. There's a difference between irregular and chaotic, but it's subtle. And this follows into another question that one of you had. Is there a critical Reynolds number for turbulence, or is it just kind of a ballpark, and what happens in the middle? And the answer is no, there's not a critical number for turbulence. There's not like some Reynolds number above which flow is turbulent and below it's just not. It's really a scale where there's a transition from smooth flow to fully developed turbulence. And that we'll get back to when we get to turbulence. I'll talk more about all those details. And I'll talk more about that in a little bit when I actually define the Reynolds number. I'm talking about it not having defined it yet because I know you guys all read it. So I think everybody did the reading. Thank you very much. I really do appreciate it. Okay, geometric similarity. So is there a formal definition for geometric singularity that the book talks about? Again, I'll talk about this again later. But yes, if all of the angles are the same between two things, but the lengths are different, these two things are geometrically similar. So if the angles are the same, but the lengths are not. So that's probably the most formal way to do it, is that basically all of the proportions are the same from one scaling to the other. It's just the overall size scale has changed. That's when you're rescaling for the Reynolds number. Is there a way to model the decay of turbulence in the boundary layer? I'm not sure who asked that. I don't remember. I didn't write it down. But yes, yes, there is, but it's outside of the scope of this class. It's a super interesting topic. The decay of turbulence is interesting, but it becomes complicated. So the book talks about, and we will show you all the different ways that these equations look really similar to the equations of E and M, especially this bottom one. The bottom one is the induction equation. It's just you swap the omega for a b. Is there deep truth to that, or is it just coincidental? There are really deep symmetries that purvey all of this. And you can derive Maxwell's equations, which derive E and M, from formulaic programmatic processes. Maxwell's equations don't just come out of nowhere. They come from very similar processes to what we're going through here. You get some kind of conservation law. To derive E and M, you have to minimize a relativistic action, which is beyond what I'm going to do in this course, but it's a worthwhile thing to do at some point in time. So the parallels between E and M and hydro are not perfect, for reasons that we'll discuss when we get to E and M, but come from similar roots. So it's an intriguing parallel, which is why I can do MHD in this course without having to do all of E and M. Let's see. Oh, at large scales, when does the gas not become a fluid? I don't remember. I didn't write the full question down, and now I forget exactly how it was worded. But basically, the question was what happens at large scale, like in outer space? So in outer space, the gas is very thin, right? There's not a high vacuum anywhere. There is no vacuum in space. Space is never empty anywhere. There's always stuff there. Sometimes the density of that stuff is 1 particle per cubic centimeter. That's low. That's a low density. That's way, way, way lower. That's 1,000,000 times lower than is humanly achievable on Earth. But it's still a fluid. Why? Because the intermolecular spacing, even though it's like a centimeter, which is really large, like normally you have like 10 to the 20 some odd particles in this kind of space, right? The mean free path, and I'll define this in a little bit. The mean free path has got to be really small compared to the size of the system. So that means if I've got a bottle and I got a bunch of things in them, the mean free path is how far an atom can go without bumping into another atom. So if that's really small compared to the system, then you can treat this like a fluid. There's some other caveats as well, but for the most part, as long as there aren't any long-range forces, if the mean free path between two particle collisions is short compared to the system, then you can call it a fluid. And even when the mean free path is 30 times larger than the solar system, if the object is 40 million times larger than the solar system, it's still a fluid. So there are big clusters of galaxies, and in those clusters of galaxies there's a plasma. And that plasma has a density of like maybe 1/10 of a particle per cubic centimeter. This means there's only one particle in like really low density. Turns out that's dodgy if that's a fluid or not, but there's a magnetic field there, and that shortens up the mean free path, keeps it a fluid. So it turns out being a fluid works pretty well for a lot of space, unless you're looking at something that's pretty small. So sometimes pretty small is like the orbit of the Earth or a solar radius. Let's see. What gives gas viscosity? I will talk about that in a minute. The disk mass was confusing. Yes, the disk mass is confusing for the accretion disk. That's okay. I might go through that stuff Thursday, kind of depending on how far I get today, but the odds are low. So don't worry about it if you hated it, but I might go back through it. Does the chemical makeup of an accretion disk impact the color and the visibility and the size and other properties? And yes, it does. But not a ton. Really, when you have something like a black hole accretion disk, the most important thing is the mass of the black hole. What it does is it heats everything to such ungodly temperatures that you can't form any kinds of bonds and nothing really has electrons on it anymore. So the chemistry really doesn't matter a ton. Mostly everything's hydrogen. Sometimes there's iron. So the iron gives you X-rays, and other chemicals give you other species, or give you other light. So you can tell that for the most part, the god-awful amount of light that we see from some of these accretion disks only depends on the black hole mass. Let's see. Oh, one of you asked about the no-slip condition. So there's a boundary condition called the no-slip condition. And it's a little counterintuitive until you think about it a while. And it shows up a lot. So if I have a wall, and I have a fluid that's moving past this wall, clearly, right here, what can I say about this component of the fluid, the component of the fluid that's directed at the wall, from right at the wall? So let's be specific. Let's call this y and this x. What can I say about Vy right at the wall?
0.
It's 0, because it can't go through the wall. That makes sense, right? So stuff can't flow into the wall, so the velocity has to be there, be 0 there. This is actually a terrible drawing of a wall because it's smooth, and you've never seen a wall this smooth. Walls look like this, right? If you're an oxygen atom, a wall looks like this. Any surface is smooth and irregular and crazy. So I can't really go that way either, because I'm going to run into some bits of the wall. Now I'm talking about like you're really zoomed in, like this table right here. If you really zoom in, it's super not smooth. It's very, very rough. And that massive roughness means that the flow can't flow across the fluid, the surface either. Now right here, it can be non-zero, but you've got to deal with this viscous boundary layer here. So the viscosity of the fluid matters in this little tiny window. These are very little regions of space. but they have very important consequences. So the material is pegged to the wall here and has to get up to speed elsewhere. Does that make sense? So when you have a wall, you can very happily say that V as a vector is totally 0 right at the wall. And this makes your life a lot easier because you can set components at the boundary to 0. So that's very handy. What ranges will the Reynolds numbers take? Reynolds numbers can range for anywhere from 0 to 10 to the 14th, depending on how big of an object you have. You can have some very interesting conversations about trying to sort out what the Reynolds number of some chunk of thing in outer space is, because it's difficult to measure. But the answer is always god-awful large. So it's like 10 to the 14. Maybe it's only 10 to the 10. That's 4 orders of magnitude, but still very large. So Reynolds numbers can be very large. Let's see. The tensor stuff, I will go through the tensor stuff slowly. And let's see, some of you had some questions about the math that I promise I'll get to. And what's viscosity? I'll promise I'll get to that. How does Reynolds number affect lift? That's such a good question. I'm not going to answer it, and I might leave it as a homework problem, or maybe a final problem. It's a great question. Okay, so let me tell you the formula for lift is something like the force of the lift is the velocity at infinity, not really infinity, just away from the wing, times the circulation, gamma. And we know what the Reynolds number is. The Reynolds number is the velocity times the size over the viscosity. I promise I'll come back to that in a second. So, the velocity and the viscosity all are related. Higher velocity, higher lift, almost without bound. So the short answer is bigger Reynolds number means bigger velocity, means more lift. Or means smaller object, less mass, more lift. And this works until you break the sound barrier, and then everything goes to hell. We'll talk about that too. So supersonic is a problem when you have lift. Actually, I'm not going to talk about supersonic lift because I don't know anything about it. But we'll talk about why it's a problem. We'll talk about supersonic flow. Okay. That is what I wrote down for questions that I'm going to talk about right now. Does anybody have other questions that are burning in their brains from the reading or from anywhere before I get going? Are we good? Okay, so today we're going to derive Navier Stokes. So what does it mean? It's big and long. It's not really that long. But there are several terms in it, and we want to understand each one. So today we're going to talk about this last one. And I'll touch on the pressure term just because I'm going to rederive that so that we're on the same page. I'm not going to talk about the left-hand side today. Maybe I will. But we're going to talk about this term first. Actually, let's talk about the right-hand side first real quick. Just so that we're starting somewhere. So I've done this before and I'll do it again. Stop me, but it's also weird and confusing, so stop me if you need me to do it again. So I want the full derivative of velocity, which is a vector and a function of x, y, z, and t. X, y, and z are also functions of t. T, we don't understand t, like as physicists at all. We don't know what's time. I don't know what time is. Time is a free parameter. Time is the way that nature devised to keep everything from happening all at once. So we just need to use chain rule. So when you're doing chain rule, we're taking the derivative relative to time, so we just have to differentiate this with respect to that, and then this with respect to that for each one of the terms. So first off, it's the partial of v with respect to t, holding everything else fixed. I don't need to write anything else down. Plus the partial of v, that's a vector, with respect to x, not a vector component, dx dt. So this is chain rule. Everybody good there? Plus, let's do the other two, dv vector, dy, dy, dt, plus dv vector, dz, dz, dt. So now, this component and this component and this component, we recognize our velocity. So what this says, this just says d partial v partial t plus vx times dv, that's a vector, dx, plus vy, dv is a vector, dy, plus vz, dv, vector, z. Well, hello.
Hi.
The only important bit you've missed is stop me if I lose you.
Okay.
So we're going over Navier Stokes, and we're going to talk about the last equation, but we're talking about the first term right now. Or math. So okay, Vx, Vy, Vz, these guys came from the chain rule, but here they are. And then I have a d by dx, a d by dy, and a d by dz, and they're all acting on v. So I'm just going to algebra factor out of v from all of this, and I'm left with vx, d by dx. This is a derivative. This is just a verb. This naked is not doing anything yet. Plus vy, d by dy, plus vz, d by dz, acting on v, and this is a vector. Everybody on board there? Now I recognize that this is two components dotted into each other. This is v, now a vector. This v came from somewhere else. It's different from this v. It's not actually different from this v, but it's different from this v because it came from somewhere else. V dot grad, that's this bit here. And grad, nabla, is the three derivatives. This is d by dx, x hat, plus y hat, d by dy, plus z hat, d by dz. So this is nabla dot v dot nabla v. So the full-time derivative, big D v, big T, equals partial v, partial t, plus v dot grad v. This is a vector, this is a vector, and this is a vector. So we'll come back to this, I promise. It's a weird thing. We'll come back to what it means in a minute. Because I've got this complicated vector operator that I'm acting on a vector. I'm just doing it one component by component, yeah.
So the vector v, where does that come from? The vx, the vy, and the vz?
Yeah.
And then the grad is the d over dx, d over dy.
Yeah, that's right.
Okay.
That makes sense. And then the v is the v that we were, this v is the v that we were originally talking about. Yeah.
The first term is a vector too, right?
Yeah, this is a vector here. So you're a vector, you're a vector. Everybody's a vector. So now let's talk about what that equals. So what is that equal to? dv dt equals f over rho. So the force per unit mass, or maybe I need it actually as the force divided by the density. Oh, that board is not centered on the camera. Let's try that. So let's do the pressure term first, just because just for the practice. So I want to know what, so this is tiny. I drew it big because I've got a great imagination, but this is a tiny little element of fluid. We want to know what the force on the surface is. We want to know what the total force on the surface is. It's going to be pressure 1 this is going to be pressure 1 minus pressure 3 plus pressure 2 minus pressure 4. That's an awful thing to write. Let's write it a little more simply. This is, we're going to call this Pij dsj. This is the force on the surface, the I component. So I did this already, so this should feel familiar, but I'm going to do it again. So this is now a good opportunity to ask questions. Pij, this is the momentum transfer. This is how much momentum I'm moving from one point to another. This is transfer. That's not an official term. That's just what it's doing. This is moving momentum around. So it's the momentum transfer in I at J. What am I going to be that? I mean, it's in the I direction, but it's at the J surface. So let's not make these 1, 2, 3, and 4. Let's make these. This is X, and it's in the X face. This is Y, and it's in the Y face. This is X, and it's in the X face too. This one's Y, and it's in the Y face as well. It's entirely possible that I could have some X along this Y face too. I will. I'll come back to that in a second. So if we just think about the pressure as you're used to it, pressure, that's isotropic, it fills space, it's pointing in every direction the same, it doesn't care about where you are. Pressure is just fills everywhere, it's a scalar. If we're just talking about pressure, then it's just going to be the one on the surface. So we take, this is a surface integral. Yeah?
Why is S only with J?
Because this is dx and this is dy. So this is, this is dax. Because this area is only pointing outward that way. So we define a little surface element. A surface element, even though it's a surface, is defined by its normal vector. Because that totally determines the surface. So we just define it by the normal vector. And each normal vector only has one component. So this is the x1, and this is the y, and then there's the z1 component. It's a good question, thank you. So why do I have 3 of these? I have 3 of these because I have 3 possible planes that I can be looking at. And I have 9 of these because I have, in each plane, I have 3 things that I could be doing. And I'll talk about what the other things are in a second. So we take this is a surface integral, but I don't like surface integrals. They're a headache to deal with because then you have to deal with a surface, and a surface is really complicated to parameterize. A volume is easier to deal with. It's just everything inside. So we turn this into a surface integral. I've got the integral of minus Pij dsj. This is a surface integral. How do I turn this into a volume integral? Gauss theorem. So how's Gauss theorem work? This is the surface integral, turns into the minus grad Pij dv. This is a scalar. This isn't a vector component. There's only so my force is then grad p integrated over the whole thing. Now I want the differential quantity. I just want what's going on inside. So df equals minus grad p dv. Okay. Now when we divide by rho, we get the p over rho. But the force by itself is just the integral of grad p, and then everything's in the integral, so we get rid of the integral. So that's the first term of Navier Stokes. Or the first term on the right-hand side of Navier Stokes. Now, okay, we're going to spend the rest of the time on the second term of Navier Stokes. So again, stop me before you get lost. That's impossible, right? Stop me shortly after you realize that you're lost. That's a better time, or that's a better sentence. So now what we want to talk about is viscosity. So here we'll define it, we'll talk about what it is, we'll talk about what it does and what it's doing in my fluid. So I have some flow. This is in the x direction, and it changes in the y direction. So it's large here and small here. So let's say that this is y and this is x. So what's going to happen? So say I've got, say I've got a jet and it's in a pool, and I turn it on, and the jet starts shooting water into the pool. What's going to happen? So I've got one part of the jet is moving faster than the next part over. It's going to accelerate this part. Why? Because it can. Because particles from here are going to move over here. Because they, yeah.
So does that mean the one below it will decelerate the one above it?
Yeah, exactly. So they're good. You're going to have a momentum transfer. I'll show you why. So why does this have a velocity? Here, let's zoom way in. This has a velocity because it has molecules in it that all have some random velocity and some bulk velocity. So I can think about the velocity of a particle as the mean velocity as well as the velocity of the individual particles. Does that make sense? So I've got some v bar plus v molecule. Also a vector. This is what the velocity of a particle is doing, or this is what the velocity of the flow is doing. So, and this would really be the peculiar velocity of the particle. This is the velocity of a particle relative to the gas motion. So this one is probably in a straight line. This is probably pretty regular, but this one is chaotic and random and everywhere. This goes in every direction. So the molecular flow, the velocity of the molecules in the fluid, and this could be a gas or a fluid, it's the same, doesn't matter. This is random. So I'm going to have some particles that are going to have a lot of this velocity, but also some this velocity. They're going to take some of the velocity from here and bring it down here, like a bucket. It is their velocity, so it is their velocity. So it's taking the velocity with it. So I've got some large component here and some small component here. This particle is going to find itself down in this lower stream with its larger velocity. So it's going to tend to accelerate this velocity down here just by the fact that it's taking some of this velocity and dumping it over there, like Robin Hood. So that's going to transfer momentum from this stream to this stream and vice versa. So lower velocity things can go from here to here. I took some momentum out. It's not in this stream anymore. It's down in this stream. So I'm transferring velocity from this faster stream to this slower stream by way of the molecular motions of the gas. Does that make sense? So we can ballpark how big this is, and this is quite hand wavy. There are many many more important things that you have to consider when dealing with like a real fluid. But if we just take, for instance, a gas, let's deal with gases for a second. How much velocity does one particle have? So let's make it an oxygen molecule, because now it's in air. Now I know what it is. What is the RMS velocity of a particle in a gas? Have you guys gotten there? So 1/2 mass of the proton times mass of the particle times VRMS squared equals what? 1/2 mv squared is energy. So 1/2 mv squared is energy. Thermal energy is 3/2 kT. If you haven't seen this before, you'll see it when you get to thermo. If you have taken thermo, you have seen this. If you have forgotten it, you should go look at your thermo notes again. But I don't need you to know this a priori, so no judgment. Thermal energy is just Boltzmann's constant times the temperature. And Boltzmann's constant is like 10 to the minus 23 joules per Kelvin. All it does is convert temperature to energy. It's a great number. So I can deal with my temperatures in energy units using K. And the 3/2 comes from the fact that the particle can go in one of 3 directions, and you get 1/2 kT per degree of freedom. We'll talk about that later. So you get 1/2 kT per degree of freedom. So if I have something that can also vibrate, that's an extra degree of freedom. This gets bigger. If it can vibrate and rotate, those are more degrees of freedom. This gets bigger, but for just one molecule of gas, can't draw that like an oxygen molecule. It's got to be a hydrogen. Because an oxygen molecule doesn't behave this. An oxygen molecule can rotate and vibrate. So VRMS is 3/2 kT. Where am I going? Talking about viscosity, talking about what the velocity of one particle is. So VRMS equals 3 kT over the mass of the particle, big square root. Okay, so that's how much velocity a typical particle is carrying around with it. That's how much energy it's carrying around with it. Think about that velocity as not just a property it has, but a amount of energy that it carries with it. And how far is it going to go? It's going to go the mean free path. So what is the mean free path? I'm not going to go through a long derivation. I'm going to skip some of it. So if I have 2 particles, so the question is, I've got a collection of gas, a bunch of particles. One of them is moving. How far does it go before it runs into somebody else? So if you think about each one of these particles is moving, there's a little bit of math that I'm going to skip. You get a square root of 2. You can look that up pretty easily. But think about each one of these particles moving relative to each other. You get a square root of 2 out of that. The length that it can go is 1 over square root of 2 times the density times the cross section. Where did that come from? Think about I got a particle, and it's going this way. It's got some cross section. What's the cross section? Cross section is very difficult to define without quantum mechanics, so we're just going to say it's like the size. Close enough. I mean, it's quantum mechanics and there's an electric field sometimes, but I don't really care about all that. All I care about is how big is that thing. So the particle has some cross section. May depend on electric field, it may depend on its velocity, it may depend on all kinds of stuff. So if we think about it's going to go a certain distance in a certain amount of time, how far can it go before it runs into something? The particles have a density of n, and my particle has a cross-section of sigma. This product gives me the length, n times sigma gives me the length that it can go, that the particle can go. Does that make sense? So let's leave that up. Let's use this board. Out of that idea. Let's this time move the camera to adjust the board. That makes more sense. So how much velocity can one particle transmit to the side? So the amount Nu, I'll talk about what nu is in a second. This is the coefficient of viscosity. You don't have anything for that right now. But this is just roughly equal to how much velocity times how far it can go. That's an A. Times how far it can go. This is equal to the mean free path times the RMS velocity. That is roughly what the viscosity is for a gas. For a liquid, there's other intermolecular forces that you have to think about. It's a little bit more complicated, but you can write it down. You'll do that in some other course. I haven't told you what this is, though. I've just told you what it is. So nu is how much velocity it can take, how far. So what we want to write down is that my momentum transfer, Pij, the book calls it pi ij. I'll do that just for consistency. Pi ij, this is equal to what? Well, we're going to just assume, okay, forget everything I said for a second. Clear your mind. I'm just going to assume that this is some number times the velocity gradient in that direction, dvi dxj. And this number is this coefficient of viscosity. Nu, this is how much velocity over how much distance. And this is also how much velocity over how much distance. So, what I want to say is F surface is equal to the integral of pi ij dsj. I'm going to say the same thing. I did this already with a pressure. I'm doing it this time with this more complicated transfer tensor.
Is that still negative?
Oh, yes. Thank you. I drop minus signs and twos like it's my job. Because it goes down the gradient. This is an important minus sign. I may screw it up, but I'll take points off if it's easy. This is a do as I say, not as I do kind of thing. Sorry. So it goes down the gradient. So the gradient, if I have something that looks like this, so this is y and this is x. So dvx dy is positive in that direction, and the momentum transfer is in the opposite direction. So that minus sign is super important. How much do we transfer? We're going to do this this same thing. What does this really mean? So now, okay, I said I was going to talk about this a minute ago. I'm going to talk about it now. Now, okay, let's think about one component of velocity. Let's just think about Vx. Now, on this surface, I can get dvx dx. So there's a dvx dx along that surface. There's also a dvx dy along this surface. There's also a dvx dz along this surface. Because the velocity, this velocity can change in that direction. It can change in that direction. It can change in that direction too, but we already took care of that when we talked about gas pressure. So this one, this is the question that everybody has about Pij being the gas pressure. I'll come back to that in a second. So on each one of my surfaces, now instead of just having a pressure that's doing its thing in that force, now at this surface I have a velocity gradient across that surface. Does that make sense? So now I got this slightly more complicated thing because it has all these terms. It has a dvi and a dxj. So this it kind of goes by really innocuously. Like it's the first thing he says, and then he talks a bunch, and then he does a bunch of math, and it gets all complicated and hairy and confusing. But this is the most important part of that derivation. What this says is that momentum is transferred linearly in a linear way. That's why this is just a constant times the derivative of the velocity. Okay, so that's point one. We like that point. It's very important. So now, this isn't quite good enough for talking about what we want to do for a couple of reasons. First is it symmetric? If I switch these two indices, do I just get to switch these two indices and get the same thing? Turns out, yes, it works just fine that way. It's perfectly symmetric. Otherwise, if you turned your coordinate system, everything would fall apart. So if this weren't symmetric, then you would be able to tell which direction things were flowing in an absolute sense. So this has to be symmetric. From a physics point of view, like if you have a boundary condition, like if you've got a flow through a pipe, not everything is symmetric, but as far as the microphysics is concerned, this has to be symmetric. But if I have solid body rotation, let's see, what do I have in here? Here we go. This is some archaic technology. As I rotate this thing, so does anybody know what this is? Has anybody seen something like this before? No. This is a magnetic tape. So you put this through a tape player, and there's a little magnetic sensor that reads what's on the magnetic tape. So this is about 20 thousandths of an inch thick, and it's like half a mile long, coiled up in here. I don't actually know how long it is, a couple hundred feet, very long, coiled up. Okay, as I rotate this thing like this, is there shear between the different layers of tape? Are the different layers of tape sliding past each other as I'm rotating like a solid body? You can just look. No, they're not. But there's still a velocity gradient from this side to this side. The center one is spinning faster than the outer ones, right? It has to be, because that's how geometry works. But there's no shear between these two layers, but there's still a derivative. So I have to fix everything to take out solid body rotation. Does that make sense? So just having a derivative of the velocity in the x direction is not shear. It's just having a derivative. Shear means things are sliding past each other, and that's when you get a transfer of momentum. So we have to figure out a way to say, well, okay, not solid body, but still this. So that's why things get a little hairier here. Super curious about what's on that tape, that it's interesting stuff. So someday I'm going to disassemble this and rebuild it. There you go. That one doesn't go any further. I guess I just got two to work with. That's fine. So what we're trying to do is generalize the velocity derivative. dvi dxj. So this is the ith component of velocity, and it's varying in the jth direction. Okay, so we got 9 things to keep track of. Just write it down as a tensor, and it's okay. What does solid body rotation look like? Solid body rotation looks like dvj dxi minus dvi dxj. This is what solid body rotation looks like. How do I know that? I stared at it a long time. I don't know, there's probably something better here that I could stick in about why this is solid body rotation. But it's like how a curl works. So curl, the curl of the velocity, I mean, it's the omega, it's vorticity, but it is also of the form dvi dxj minus dvj dxi. This should be familiar to everybody. If not, holler and we'll talk about it. This is what a curl looks like, and you know that the curl is the rotating parts. Right? Okay, so we got to get rid of this. How do I get rid of this? Let's do something clever. A equals 1/2 A plus B plus 1/2 A minus B. One of the most magnificent things about doing math proofs, is adding 0 in the most complicated way possible. And that is what we've done. So does everybody see that this is true? So if I just expand this out, I got a 1/2 and a 1/2. They add up to make my whole. And I got a 1/2 and a 1/2, but they have different signs, so they cancel each other out. So the viscosity that I want to deal with, we're going to use that. Okay, this is the thing that I want to deal with. I want new dvi dxj, but we want to generalize this a little bit so that it doesn't have some of the crap in it. This is the crap in it that we want to get rid of. So we'll just use this fact to turn this into something else. So dvi dxj is equal to 1/2 dvi dxj plus dvj dxi. That's the backwards. I and j, you got to keep track of which one's where they are, and whether they're I, j, or k matter. So I on top, j on top, j on top, I on bottom. Minus 1/2 dvi dxj minus dvi dvj dxi. Okay. Is everybody on board with why I did it this way?
Should be plus 1/2.
Thanks. Is everybody on board with this? If not, speak now or speak later. So this is the general thing. Okay, so this is really how we thought about it. And the reason that I'm kind of going slow through this is because I want to make the connection between using words to describe the thing. Shear transfers momentum. Those are the words. When you have a shear flow, momentum goes in the opposite direction. So that's the math. That's the concept that we're working with. The math, the first step of the math is this, just dvi dxj. That doesn't work good enough. I'm not an English professor, so no comment. What we're going to use is dvi dxj equals 1/2 dvi dxj minus plus dvj dxi plus 1/2 dvi dxj minus dvj dxi. Plus minus j I. Okay, kind of complicated, but has some symmetry to it so that you can kind of write it down just by thinking about it. So this is a more general version. This is a more general version of this. So now we just need to integrate. Well, not yet. This isn't generic enough, because this isn't rotationally symmetric yet. I haven't forced this thing to be rotationally symmetric. What does that mean? So I've got, this is a tensor, and I have xx, xy, xz, yx, yy, yz, zx, zy, zz. Follow that. So this is just a square matrix of all of these terms. And there's really, in a matrix like this, there are two kinds of elements. There's the ones on the diagonal, and there's the ones off the diagonal. You can tell the difference there, and they've got to be related, and they've got to be rotationally symmetric. There can't be anything that's different between x, y, and z. So this is I, this is j, this is k, this is j, this is k, j. So it needs to be rotationally symmetric, and there's kind of two, as I rotate, if I swap I, J, and K, I move these guys around, but these rotate amongst themselves. That makes sense? So this, think about this as a tensor. We'll just call it A, I, J. As I rotate, if I change I and J, when I is equal to J, that's these components. So if I change X to Y to Z, these guys swap amongst themselves. And if I change X to Y to Z, these guys swap amongst themselves. Does that make sense? So we've got the diagonal elements and the off-diagonal elements. So the diagonal elements all need to be rotationally symmetric, and this is dvi dxi. This is equal to the divergence of the velocity. So the divergence of the velocity has to show up by itself, because I can't have dvi behave any different than dvj, right? Any different from dvk. So the only way for this derivative to make sense is if they all show up at the same weight. So this is dvx, dv dx, dv dy plus dv dz all added together. So div v represents the diagonal of the tensor. And the other ones are the off-diagonal elements. So I wrote it down this way. I'm going to write it down in a slightly more general way. Okay, this is what I just say. This is my hypothesis. This is making it a little bit more general. Now we need to make it rotationally symmetric. So okay, dvi dxj wrong notes. Sorry, let me do that a little differently. So my generic transfer tensor, ij, we want it to be some number times my gradient. Now I can separate out my off-diagonal terms from my diagonal terms because they're gonna rotate separately. So we're gonna write this as some number a times vi dj plus d vj di dxi, let's leave the x's for now, plus b times div v. We've gotten rid of this term. We threw it out. We don't want that part. We only want this part. Does that make sense? So we throw that part out, and we're just going to hang on to this part, because this part is rotation, and we don't want the rotation. We just want the shear. So the most general thing we can write is a times dvi dxj dvj dxi, that's the first symmetric part, plus b times dvi dxi. So this is for where, oh, well, no, this isn't. This is for where I and j are the same, but I and j are the same are still here. Does that make sense? So when I flesh out, I fill out what I and j is. If I'm going to make a table of what this is for every I and j, I'm just going to go right down, I'll just go fill out I and j for 0, 1, and 2, or x, y, and z. There will be a dx, dx, a dx, dx here, too. We don't really want that. We got to get rid of that. Okay, hang on one second. The other thing is that we already talked about what the momentum transfer is in one of the directions. We already talked about one of the directions. We already talked about the pressure. We already talked about the longitudinal part. So this is the compressive part. This is the three-dimensional rotationally symmetric part. So pi I have repeated an index. So what does that mean I'm doing? Summing. So I've repeated this index. So I'm adding up all the three-dimensional elements. This is going to go back to my little control surface. We're going to look at, we want to know what F net is on this. We talked about what the pressure is. The pressure is Vx in the x hat face. that's the pressure, is giving me changes in Vx along x. This is the one we dealt with already. And then I've got, in this face, this is changes in Vy along y hat. And then now that the board is changes in Vz along Vz hat, and we took care of those in the pressure already. So we can't do that again. So the trace of this has got to be, well, there's three terms. This has got to be equal to the gas pressure. And there's a 1/3 there because I've got three of these. Wait. Sorry. I think I have brain farted. I'm going to cheat. I'll look in the book. Because there's three of these. So you want 1/3 of them. Double check and then I don't screw up. So we know how the trace of this thing should behave. Let's see. Is there anything else? So I've taken care of the longitudinal pushing. So I push this way with gas pressure, the velocity accelerates in along the same direction. So we've taken care of that direction, so we need to not have it in here. So what that means is, so my total, we've taken care of the pressure of the gas pressure. Actually, this should be a PIJ. I'm mixing the notation here, sorry. My pressure tensor is P gas. So that means that pi II, my transfer through viscosity, II, I'm summing along the diagonal, that has to be 0. Because we've already taken care of, remember what we were talking about? This is the transfer of momentum in the I direction, the I component of momentum in the J direction, but the X component of momentum moving in the X direction we already took care of with pressure. Pressure does that. Pressure gets to do that. So that's the micro motions of things moving along that direction. So I've got a wall. It's what I feel from my particles slamming into the wall, into the same direction of the wall. This is my wall in X, particle motion in X. We've already taken care of that. So the trace of this has to be 0. So that means, okay, if I sit down and I write out I, that means that I have to have 1/3 here. So in the most general thing, these two numbers can be different. So my off-diagonal and my diagonal elements can vary slightly differently. But since I've already taken care of the pressure, then they have to be this. Then they have to vary in concert with one another. So this becomes 1/3. So what happens is this we'll call nu, and we'll consume this into this. So we'll just have nu again, dvi dxj plus dvj dxi plus, minus 2/3 div v.
And is this expression pi I or pi ij?
This is pi ij. Pi I is 0. But you'll see if you set I equal to I and add everything up, you get 0. Okay, not done yet. All right. So thinking about it, making it more general. Taking out the pressure bit. So now the momentum transfer of the I component in the J direction, that's how we read this, and it's symmetric, you should get it the other way as well, is equal to minus nu times dvi dxj plus dvj dxi minus 2/3 div v. So div v and the other twos are treated separately. Okay, it's a lot of work. You don't have to go through all this work when you're deriving it, but I'm going the slow way and saying everything like 40 times. So once you go over this again, there will be a homework problem. Do this. When you're doing this, you don't have to go quite so slow and be quite so painstaking. You can just say, this is what I want. This is more general. This is I need to do because of this. You don't need to spell everything out quite so slowly, but you might need to because that's where you're at. Okay, so we're not done yet. I'm going to throw another thing out of this. I'm actually going to throw away two things. And actually, this kind of drives me nuts because what we're really doing is deriving something that we're going to throw out because what I'm going to do now, this is the momentum transfer, so df surface is the integral of the surface of pi ij dsj. This is let's just call that dfi. It's just the integral of pi ij over all the surfaces. What am I going to do with this? It's a surface integral. Surface integrals are a headache. Let's turn it into a volume integral. I get another derivative. That should be comfortable by now. But if not, it will be later. So now we'll turn this into a volume integral of d pi ij dx. What goes here? I or j?
J.
Why? Because the surface is j. You can think about this way. This is df, f dot d, a. This dot product is relating the components of this with the components of that. So the vector component of here is where the grad comes from. I don't know if that was helpful. What's this? D volume. Okay, so let's do that. Now we've got df is equal to, I need a bigger chalk. Actually, I want to write this in red. So df is now equal to d by dxj of nu times dvi dxj plus dvj dxi plus minus 2/3. I'm going to be explicit here, dvi dxi. Okay. Now, so this is an equation that you're never going to need because I'm not going to ever deal with things where nu is not a constant. So nu, we talked about what nu is. Remember, nu is the free mean path times the RMS velocity. We'll do this integral. So now we're going to do this integral. We're going to put this into here. Let's simplify a little bit. So nu comes outside because it's constant. Yeah.
Is there any reason why there's no I on the df?
Thank you. Minus sign too. So this times this is nu times d bi dxj squared. And this times this is again div v. This is dj on vj. So then this becomes plus 1/3 div v. So this is 2/3 div v here, and it becomes plus 1/3 because of this other thing. So what we're left with is something that looks quite a lot like what we started with, but we went through a lot of algebra to make it a little bit hairier. So the important bit is I've got something that looks like this. This is what's happening on the surface, so I use Gauss's law to turn this into a volume integral, and I get another derivative, and that's where the del squared comes from in in the Navier Stokes. Yeah.
So what is it at the bottom? It's kind of hard to read.
Yeah, I'll do that again. Okay, so this turns into dfi. Now we've got a volume integral is nu times del squared v plus nu times 1/3 grad div v. So just for the hell of it, we're going to throw out that whole second term too. So now we're just left with this. Why do we get to throw out this term? Well, okay, div v. We haven't talked much about div v yet. But if I have an incompressible fluid, div v is 0. Like a lot 0. Like Maxwell's equation is 0. Div v is super 0 if I have an incompressible fluid. And my fluid is basically always incompressible. So we can throw out this term. This is called the bulk viscosity. And it shows up, and I probably need to deal with this more professionally because I do a lot of supersonic fluid dynamics, and I skip this term too. So lots of people throw this term out. I throw this term out too, though. So I throw a lot of stuff out. You got to be really kind of clever when trying to get computers to do physics. Okay, so where do we go? This is kind of a long path. We're talking about transverse momentum exchange. Oh, and I got 2 minutes left. This ends at 2:35, right? Mm-hmm. Got 2 minutes left to recap, so that's perfect. So this is the assumption. This is what we just say. I think it looks like this. Momentum transfer is transverse to the velocity direction from molecular stuff, and it's going to be linear to the velocity. Okay, this isn't general enough because we got to take out solid body rotation. So we take out solid body rotation, and that's where this gets kind of hairy. Then we need to generalize it to make it rotationally symmetric. My physics needs to not care which direction I'm pointing in. So that simplifies this. So we got to take out the rotation because we don't care about that, and we'll generalize this a little bit, and we're left with this. dxi, dxj, dxj, dvj, dxi, minus the diagonal term. We take off the diagonal term because we were already dealing with the compressive part with pressure. Then we do Gauss's law again to get nu del squared v plus nu times 1/3 times div grad v. You're never going to need to deal with this term except when you're deriving it and you get there and you say, oh, that part goes away. So that's the important bits of this derivation. The important bits of the derivation in my head are making the assumption right and doing this last stage of the integral right. You can screw up a couple of things and they fall off and you don't matter, and it doesn't matter because we throw them out anyway. So a lot of this derivation is to get this right, but we throw that part away. If you really need it, it's important. So that's where Navier Stokes comes from. So dv dt plus v dot grad v, this is the time derivative, this is the full derivative, equals minus 1 over rho grad p, so that's the gas pushing on itself, plus nu del squared v. This term is the new one today. This is the viscosity, and this is shear flow. This is momentum transfer because of shear. This is where all the energy goes. If I don't have this term, energy stays in the system. This is where energy gets dissipated. This has a lot of interesting physics with it that we'll talk about. Now I've written down an equation that if you could really solve this, if you could really write down the solution space to this, you'd be famous. Because I have one term, this term here, I'll show you later, but this term makes things blow up like crazy. Like if you simplify things, this term just makes everything blow up. Why? think about if you're ever in traffic and the guy behind you is going faster than the guy in front of you. Think about it for a second. Unless somebody stops, you're kind of hosed. So what this term does is makes things blow up, because it's the derivative of the velocity along the velocity. I'll talk more about this later. This is the derivative of the velocity along the velocity. So this is changes along the velocity. This is where things blow up. But this term washes things away. So this term is really well behaved. The diffusion term makes big explosions go away, and this one makes big explosions, and we don't know if they cancel out or not for every situation. There might be situations that Navier Stokes blows up, but we haven't found it yet. But we also can't prove that it never happens. So I'm not suggesting that anybody works on that, because I think that that's a bad career move, because it is literally impossible right now. Nobody else can do it. So that's what I got for the day. Homework due Thursday. Office hours tomorrow at 4. Does that work for everybody? If I have office hours at 4? All right.
Oh, Professor, I have a logistical question.
Okay.
What date is our final again?
It is Thursday at 12:30, I think.
Okay, thank you.
Planning your departure.
No, it was something to do with another class doing final dates